Hi everybody and welcome to Chem Talk, where today we will be going over Dalton's law of partial pressure. In addition, we will discuss how it applies to a function as common as it is important, breathing. So let's get into it. Let's begin with some definitions and introduce the law we will go over. Pressure, in terms of chemistry, is the amount of force exerted by gas molecules as they move about an enclosed space. The kinetic theory of gases states any gas will diffuse to completely fill the space of an enclosed container it is put in. When mixed with another gas, the gases will act independent of each other and not be attracted to one another. And now for the actual law. Dalton's law of partial pressure states that pressure total equals the pressure of A, pressure of B, so on and so forth. So all the collective pressures combined. In other words, the overall pressure of a system is the sum of the individual pressure each gas is exerting on the container. The mole ratio of a gas in a mixture of gases can be used to determine the partial pressure of that gas if the total pressure is known. For example, if you have a mixture of 3 moles of nitrogen and 4 moles of oxygen, knowing the total pressure in the container is 8 atm, and you want to find out the partial pressure the nitrogen is exerting, you can use the mole fraction. The total amount of moles is 3 plus 4, which equals 7, and the fraction of nitrogen is 3 moles out of the total 7 moles. This ratio matches the ratio of the partial pressure of the nitrogen and the oxygen. So let's create an equation. 3 moles of nitrogen over this total 7 moles is equal to x atm, which would be the partial pressure of the nitrogen, over 8 atm, which is the total pressure. 7x equals 24, and we get x as about 3.4 atm. So the partial pressure of the nitrogen gas is about 3.4 atm. Let's try another example. We can also use known pressures and volumes to find the partial pressures of two gases after mixing them. Let's say we have 12.0 liters of nitrogen gas at 4 atm and it is mixed with 10.0 liters of oxygen gas at 6 atm, and these are combined in a 15.0 liter container. Both containers are at 273 Kelvin. Find their partial pressures and the total pressures of the new container. We can use the ideal gas law. Pressure times volume equals moles times gas constant times temperature, to calculate how many moles of each gas is present. For nitrogen, we fill in 4 atm times 12.0 liters equals N times 0.0821 times the temperature of 273 Kelvin. That gives us 2.1 moles of nitrogen. For oxygen, we fill in 6 atm times 15.0 liters equals N times 0.0821 times 273, and that gives us 4.0 moles of oxygen. So our total moles of gas are 2.1 plus 4, which equals 6.1. Now we want to calculate the total pressure in the new container and use the mole fraction method to get the partial pressures after. Our total pressure is pressure times the volume, 15.0 liters, equals 6.1 total moles times 0.0821 times 273 Kelvin. That gives us a total pressure of 9.1 atm. Now to find the partial pressure of the nitrogen gas, we say there's 2.1 moles of nitrogen over the total 6.1 moles, and set that equal to x over 9.1 atm, where x is the partial pressure of the nitrogen. So x equals 3.13 atm. For the partial pressure of the oxygen gas, we say 4 moles oxygen over the total 6.1 moles equals x over 9.1 atm, and the partial pressure of oxygen is 5.97 atm. We can check accuracy by adding these partial pressures and making sure they add up to the total pressure. 3.13 plus 5.97 equals 9.10, and our total pressure was in fact 9.1 atm. Now we can discuss the real-world applications of this. In, air fills small air sacs in our lungs called alveoli, but the air we breathe in contains many components, not just oxygen, like nitrogen. So oxygen has some partial pressure in the lungs. So it then becomes important to note that the partial pressure of oxygen in our lungs changes based on our relative elevations. For example, at sea level, the partial pressure of oxygen in the alveoli is about 0.21 atm, while at the top of Mount Everest, it's only about 0.07 atm, where the air is thinner. Dalton's law allows us to make these calculations, which become important to note for people who are going to extreme elevations, whether it be on top of mountains or far below the sea. So that's all for today on Dalton's law and partial pressure. Thank you for tuning in to ChemTalk. Make sure to visit our website, www.chemistrytalk.org, for hundreds of general, organic, and biochemistry articles.